So now we're going to finish chapter 29, this last packet, and we're going to start off with Amperes Law. This is the beautiful magnetic equivalent of Gauss's law. So let's take a look at it. All right, so Gauss's law was the surface integral of E dot dA was Q enclosed over epsilon naught, and that was equal to phi E, the electric flux. And so here with Amperes law, you can see it's different. So now we're not dealing with a surface integral, we're dealing with a line integral. The way you can tell that is if you look at, it says B dot ds. Right? With Gauss's law, it was dA. So we're looking at an area, so we're looking at a surface. ds is some path. So if you take some loop, right, the integral of the little pieces, B dot ds, of all the little pieces around the magnetic field, dotted with each of those little pieces around some loop, that's equal to mu naught, right, the permeability constant, times the enclosed current going through that loop. And that's it, right? It's a beautiful little law, and it allows us to calculate the magnetic field in a bunch of different ways, right? Because ds, if we make ds just the loop around the edge of a circle, we know that that circumference is 2 pi r. And so, let's see. And so if we've got a magnetic field going directly out, or something like the wire there, then we can see again, B equals mu naught I over 2 pi r. That's like what we had before. That's verifying, the magnetic field around a circle, because there we're adding up B is in the direction of that circle, right? And it's a dot product. So we're adding up that full magnetic field around the circumference, 2 pi r. And so then what we see is that B dot ds, right, is equal to mu naught I. So it's a way of looking at Amperes law. So then if we use that, we can take a look at the magnetic field where we're inside of a wire, and A is the perpendicular distance between the wire and where the field is to be calculated. So inside and outside, you don't have to go through the derivation. You're not going to be asked to do that, but you can see, right, we skip down to where you see that graph, that B is given by mu naught I over 2 pi big R squared and then little r on the top. It looks just like the stuff that we saw for magnetic field, for electric field, inside a solid insulator or a solid body for the gravitational field. And then B outside is what we had before, mu naught over 2 pi r. And now we're going to look at the magnetic field due to a long solenoid. Long, right, means we don't care about the distance. It's infinitely long as far as we're concerned. And so there what we're doing is we've got all these little loops, right, lined up next to each other, so that this thing looks like a large cylinder. Okay, and so it's B equals mu naught I n over h, capital N over lowercase h, where h is some distance, and n is the number of turns within that distance. N over h can be substituted with a lowercase n, which you see there, and lowercase n is just the number of loops per unit length. So that's inside a long solenoid, and we're going to be seeing that quite a bit. Solenoids are going to play a big role in the next chapter, chapter 30, where we start putting these things into circuits and seeing how that affects, how circuits are affected that way. Short solenoids, we're just going to look at this really briefly. In reality, the magnetic field is not constant in the solenoid. Instead, it gets bigger in the middle and then drops off at the edge. And we're going to skip example 10, because to do this we would have to go into the current density to get the velocity, and then use the velocity to find the current and all that other stuff, which is not really necessary. Okay, a toroid. A toroid is where we take a solenoid and we turn it, right? I take some coil, not a coil, the solenoid, right? It looks like a helix, tightly wound, and I make a donut out of it, a donut shape. And so within the solenoid, B equals mu naught I n over h. But now that we've made kind of a circular thing out of it, the h is replaced with 2 pi r. And so we end up with B equals mu naught I n over 2 pi r. R is the radius, because that's the length, right? And it's continuous, so we're not dealing with, at the end of a short solenoid, it dropping off or anything like that. And so a current carrying coil produces a magnetic field like that of a bar magnet. And again, a current carrying coil is just, wrapped around, it's just like a circle a bunch of times. And a coil is not like a solenoid. Solenoid looks like a cylinder. Coil still looks like a circle. Magnetic flux. Okay, so here it is. Magnetic flux is B dot dA. This is not what's in Amperes law. Amperes law is B dot ds. It's a loop integral. But here we do have an area integral. And so now we're looking at magnetic flux. We had electric flux, now we're looking at magnetic flux. And so this is the magnetic field dot product with the area vector. So it's BA cosine theta. And so really simple example, example 11. Calculate the magnetic flux through so we should talk about the units of this. It's a Weber, right, where it's Tesla meters squared, but it also ends up being Tesla, or since a Tesla is a Newton per ampere meter, this ends up being a Newton meter per ampere. Okay, so if that makes any sense to you, keeping track of units and stuff like that. The magnetic flux through a current carrying wire, if the area vector is 2 in the I direction and B in the I direction, these two things are parallel, and so the flux is going to be, cosine theta, theta is 0, so cosine theta is 1. And so all we're doing is multiplying 2 square centimeters, which is 2 times 10 to the negative 4, times 4 times 10 to the negative 4 Teslas. And so we end up with 8 times 10 to the negative 8 Webers, or Tesla meters squared, or whatever other units we can substitute at this point for that. All right, and now here's another one. Calculate the magnetic flux through the current carrying wire that has area vector 2I plus 2J centimeters squared, and B is 4 times 10 to the negative 4th. And so B dot A, well, the only part of A that's parallel with B is the 2 times 10 to the negative 4th part. So that's the only part that I care about. And so I end up with 8 times 10 to the negative 8 Webers. Okay, the way that we do dot products, remember, we multiply the things that are in the same dimension, and then just add them together. And here it ends up just being 8 times 10 to the negative 8 Webers, or 8 times 10 to the negative 8 Tesla meters squared, something like that. Okay, and so then it's important to recognize that magnetic fields are caused by currents in conductors and also by changing electric fields. So if I have the full piece of Amperes law was then perfected by the Maxwell law, so it's the Ampere-Maxwell law. There's the generalized version of Amperes law, that if I have a changing electric field, then that also creates a magnetic field, and that's what happens in light. Light, you have a changing electric field, and then that induces also a changing magnetic field, and so light is a electromagnetic wave. And that is it for chapter 29.